Very good morning to everyone. And first of all, I think I'm very honored as well as it's a pleasure on my part to be presenting here. And thanks to Professor Masalam and his team, peer team, for inviting me to present this work. Because fire is a significant hazard to the built environment, as we all know, and it does a lot of damage and destruction throughout the world. Unlike, for example, earthquakes, which is in one part or one region, or for example, hurricanes is in one part, or if you do look at cyclones or winds only in the Midwest United States, fire does damage in each and every community around the world. Now, I would like to first acknowledge my PhD student who just completed and who is working in San Francisco here, Ankit Agarwal. He was here yesterday, he is not here today. Now, the title of this is Conditional Assessment of Fire Damage Structures from Reconnaissance to Advanced Analysis. As I said, fire does damage not only to the people, but also to the animals, as you see in Australia, or it does damage to the environment significant, and in addition to that, to our structures as well. But resilience, when it comes to fire-induced collapse, we call it, resilience under the fire hazard is very much neglected or not even considered in any design or analysis. So I'm going to give you a little bit of background to the magnitude of the fire problem, then present how typically concrete structures. I'm going to focus a little bit more on concrete structures because it's much more complex, and also the residual capacity is much more retained in concrete structures most of the time. So I'm going to focus on that. Other structures also face the same problem. And what is the need for evaluating the residual capacity? And then present a classification of damage which can be done through basic reconnaissance, and you can go through to advanced analysis how we can classify structures of the fire damage, which is very important, and there is lack of guidelines or standardization for this. And then present a methodology which we are developing as part of the PhD work recently and advancing it. And if possible, I want to present a case study, but let's see. Now, fire represents a severe hazard and threat to the built environment, as I already said. And these fires cause thousands of deaths and billions of dollars of damage every year in each and every country around the world. If you look at the statistics for the United States, there was more than 1.32 million fires in 2017, ranging from very small fire to a very large fire, okay? Caused 3,400 fire deaths and resulted in $23 billion of losses. And if you include indirect losses, it adds up to more than $50 billion. In any country around the world, fire damage or fire losses is 1 to 2% of the GDP every year. Okay, just to give you some statistics. And good thing about this also I would like to add, many of the fires don't lead to collapse of structures, collapse of the damage, and even, it is put away very easily. But there are a good number of fires which do cause damage and destruction. Now, fire is an important event or an hazard. Why? Because fire can start due to an electric short circuit in any one room. There are so many electric outlets, it can start from there. It can start in a kitchen, for example, or somebody throws luckily, smoking is banned in most public places now. Before that, most of the problem in the United States till 80s was smoking. A cigar falling on a carpet or starting a fire. Now, that's one thing. But the secondary event, after earthquakes, you saw what happened in Kobe earthquake. Right? And even in Chile, in the recent earthquake, there were fires after that. New Zealand, for example, or San Francisco. We know in 1906 what happened in San Francisco. Fire did much more damage than the earthquake itself. So as a secondary event, after an earthquake, after a blast, truck hits a bridge. You are designing that bridge to resist that impact load, but forget about the fire. Including in 9/11, much of the damage was done by fires, not by the planes hitting the building. In fact, the conclusion, I was part of the investigation team on September 12th, we were at ground zero, but the conclusion of this report which went to Congress was the towers would have been standing today if there was not that kind of fires or if there was no severe fires. Okay, so fire as a secondary event will be the primary cause of damage. Now it can happen even, you might laugh at this, after a flooding where more than 1,800 homes were burnt down after Hurricane Sandy. in New Jersey because electric short circuit in one basement led to each house was $1 million plus or $2 million, 1,800 homes. So you can imagine the damage. Now, to mitigate, we put in lot of measures. One good thing why you don't see fire leading into collapse is because we put in number of measures. Fire prevention, we try to prevent by making those electric short circuits much safer, much this thing. Then we put in sprinklers, heat detectors, smoke detectors, exit paths, number of them. And the last one we put in is called structural fire safety. That means a building has to stand up for 2 hours, 3 hours or 4 hours in case if there is a fire, so that the fire can be put out and the building can be back to normalcy. Now, this structural fire safety, okay, is based on prescriptive approaches. Yesterday, as it was mentioned, in most building design, it's based on 100 years old or more than 100 years old. So each is not engineered at all, unlike other events. The second problem is only very limited number of fires grow into full-size fires. That's a good thing. But you cannot send people into occupying that building, or you cannot open that bridge for traffic after a fire unless you know that it's okay. Otherwise, there is a lot of issues with respect to liability and stuff. So there are no methods or lack of methods for assessing the residual capacity of structures. That's one part of the equation. So this is very important aspect and very little advancement in this area. Okay, so look at the high-rise fires in buildings. I'm just pointing it out to show them, illustrate the magnitude of the fire problem. Starting from 9/11, where more than 40 buildings suffered damage and destruction. Out of this, about 9 buildings collapsed, 18 buildings suffered damage, and much of it is due to fire. Okay, and things have not improved since then, though there are very limited changes in the codes. Windsor Tower, for example, I was part of this investigation at Technical University of Delft Reconnaissance team, wherein a short circuit in a coffee kettle led into fire. This 13-story building, architectural building, collapsed. Right after that, one of the biggest problems in that was whether to get into the building or not to assess the damage for a number of days. No techniques, no technologies. Right? So then let me talk about Grenfell Tower. This happened as well in Paris as well, but lack of time, so I will look at Grenfell Tower. Grenfell Tower, a lack of wiring or faulty wiring in a fridge leads into a huge fire. And because of the outside, the combustible materials of the cladding, fire spreads very rapidly, never seen that kind of fire. But when this number of people were there, and definitely fire affects much more people who are poor, people who are vulnerable, people who are aged, because they cannot run away fast. So in this building there were a lot of refugees and others, I think, and those people, they didn't have lack of understanding, including the language problems, to get out of the building. When they were trapped, the biggest problem was firefighting happened, but that could not be controlled. But firefighters, then they withdrew. They couldn't get into the building after 2 or 3 days, because they never thought the building was safe. And structural engineers couldn't do much because to assess the damage. So because of this, it took 3 days even to recover the bodies or to get into the building in case if somebody was there to save them. So this is how it turned out. Now, it is not buildings alone. In case of bridges, it's worse because that's the most infrastructure you need. Why? In the case of the buildings, we put in lot of measures for at least getting this fire under control or fire problem under control, like sprinklers, heat detectors. You don't do anything, including those bridges are not designed for fire at all, or no prescriptive approaches even. Today in US, you don't need to have any measures for a bridge to be built from the fire perspective, whereas in buildings you need to do that, right? Building codes are very specific. So when you look at this number, including the MacArthur Maze, you all know it happened right next door here in Oakland area. And in this case, a steel girder bridge, 17 minutes the bridge collapses. It's a textbook kind of failure. I teach a course. I tell my students steel structures, 20 minutes it can collapse without any fire. Here it happened in 17 minutes because it's an oil fire. I teach building fires, right? So in this case, you see what happened. How much loss to the economy. It took weeks or months to rebuild this bridge. Silicon Valley people were asked not to come to the work for the next few months. Okay? Now let me tell you if concrete bridges are better. This is an example. This happened outside of Atlanta Airport or close to Atlanta Airport, I-85 and I-85. And this bridge, what happened was there was a problem with the drainage. So they decided to put in lot of pipes, brought in lot of pipes, and those pipes were basically polyvinyl chloride pipes, so that in the spring they can start the work. On a March evening, when it was very cold, so a homeless person comes in, and that's at least alleged. Okay, he comes in and puts lot of papers around and rubble around for fire to warm himself up, and it spreads, he runs away. Then when the fire department comes in, they start to fight the fire, because it was in a highway, it was close to Atlanta, so they could come, fire department. But what happens right next door? Look at, they couldn't fight the fire because of the new kind of materials, new kind of constructions where we are increasing all these durability characteristics and concrete strengths. Today my students are making 35 KSI. 200 megapascals of concrete, 220 megapascals of concrete, it explodes under fire. That's a different topic for some other day. Steel is not, also new types of steels have problem. Wood is much more problem. Any new material you tell me it has lower fire resistance than what traditional materials used to be, including masonry. So anyway, look at this, what happens. Okay, huge fire, firefighting could not happen, lot of spalling. Can you see that reinforced concrete completely exposed? The problem was not that multiple spans happened, few spans collapsed. They didn't know which to replace, which to rebuild, because it takes a lot of work to take the course and test it and stuff. So there is not much methods. How are we doing right now? So right now concrete structures typically have excellent fire resistance, and in most cases they recover much of the capacity. Right? Much of the residual capacity is there in the concrete structures. Typically, we don't have to do anything in concrete structures from fire design. All we need to do is provide that concrete cover to the reinforcement and making the members minimum dimensions. That's the current code. And with temperature, the strength and stiffness drops. This is concrete, that's steel, this is wood. So concrete typically loses strength much slower than other materials. That's the property which gives it much better fire resistance. Our residual capacity is left. If you look at this 9/11 buildings, this is the World Trade Center 7. After 8 hours of burning, intermittent burning, it collapses. It was designed for 2 hours prescriptive approach. Look at the concrete building 90 West, burnt for 5 days intermittently, designed for 2 hours, it could be retrofitted. This collapsed, this could be retrofitted. So concrete structures, just a message is, can retain significant amount of capacity. As I mentioned to you, it's very important from the residual capacity assessment after a fire incident happens, because first thing is whether you want to send those people into that building where they were in the apartments, because otherwise, a building might collapse. It happened in Switzerland, a parking garage was there. After 48 hours nearly, people went back, as firefighters went back to the parking garage, building collapses on them. Because cooling phase in lot of fires in post-tension structures is much more dangerous than during the fire itself, when it's cooling, right? So now, it's not only that, what kind of repair, how much capacity has to be restored? You need to do calculations, you need to find out the residual capacity, as well as from insurance and damage assessment, from the state agency's point of view or insurance company's point of view, it's very important. What is the current state of the art? Very, very, very limited. Based on through prescriptive approaches, I think there are some guidelines, such as UK Concrete Society has some recommendations, and the books, there is very limited information how to assess damage, and American courts doesn't even have any information, including the new ACI repair code when it comes to fire damage. Now, why is it so bad? Because of the complexity and also limited research which is going on in this field. So what happens if there is a building under fire, if this beam, if you take, where there is fire in this compartment, during the heating phase, this is how fire starts and it cools down. And the temperatures within that concrete beam or concrete member, this is rebar temperatures, this is concrete at mid depth. Now look at the structural deformations. So lot of damage is happening in the structure, but it's recovering, and at each minute various properties in the concrete microstructure steel, it is changing. That has to be accounted for the analysis, and finally you end up here after the complete cool down of the structure, which takes day, 2 or 3 days. So look at this. This is the residual deformations, which has an impact on the residual capacity. There is, as I said, very limited information in the current codes and standards, and so we came out with a classification system wherein if there is a fire in a building, bridge, anywhere, you can classify the structure, overall structure or structural members into 5 levels of damage. Class A, when there is very limited or no damage at all, cosmetic damage, just the paint is gone or something. To class B, technical damage, very small cracks and stuff. To minor structural damage, yes, there may be loss of capacity really. To some level of capacity and significant level of capacity. Okay, class A to class C. And then we came out here, no analysis needed. Just some reconnaissance based on the first everywhere reconnaissance is needed. Then you move on to simplified analysis, just can be applied to fix those cracks or whatever. And here you can apply simplified analysis to some non-destructive testing. Here some semi-destructive testing. Here you need advanced analysis together with NDE or NDT methods. Okay, then you decide whether to facilitate reoccupancy or demolish. In most cases here, there is a chance you may have to demolish, but in these cases you can retrofit it very quickly and very easily, whether it's a bridge or a building. Now, as you can see here, in fires, only severe damage happens 8% of the time. But some statistics show under 55% of the dam, after reconnaissance, you can say that there is not much you can do, or there is not much damage happen to the structure, but you need to look at it carefully. So this is some description or explanation. What is conditional assessment? Reconnaissance mean just field inspection, observation. Some expertise can do it, go into the site immediately following the fire. But non-destructive testing, because you can do this, some Smith hammer and other kinds of tests. There is some information, semi-destructive testing, and you can apply some empirical approaches such as simplified analysis when the damage is class D, but E, you have to carry out advanced analysis. Now, even in the same building, as you can see here, you can have various classes of damage depending on where you are in a building. Some parts of the building may be class A damage, class C damage, class C damage. So this has to be done from the first reconnaissance to do more deeper into this. So reconnaissance is the most important step. Now, advanced analysis, let me get in directly to the approach. This is the approach we developed recently. I will just show you quickly because of lack of time. You need 3 stages of analysis. You need to know just before the fire what the structure was, because structure might be designed for overcapacity, which we always do, but what was the condition just before the fire started. Then second step of the analysis or stage of the analysis is during the fire, what happens. Especially the complication is during the fire heating phase and cooling phase, where the properties, your boundary conditions, everything are changing with time. Okay, boundary conditions especially are very important. And during the third stage is just after the fire, after 2 days or 3 days, what's the capacity. Okay, so 3 stages which in the literature nobody talks about this. So this is a new approach we developed, and the problem is at each step of the analysis, for each stage of the analysis, the material properties are different, boundary conditions are different, failure limit states are different, remember. So that has to be given due consideration. Once you do this, okay, just to show you, for concrete, see, look at this, during elevated temperature, when the temperature is in the heating phase, the stress strain curves is decreasing like this. In the steel, it's decreasing at 800 degrees here, 20 degrees here, but steel recovers much of its strength, whereas concrete doesn't. Okay, during the cooling phase. So this is the yield strength or compressive strength. Concrete doesn't recover. This is during the heating phase. This is during the steel, recovers much of it. So all this is very complicated from that point of view. You can apply finite element models, which I'm not going to go into this. I'm going to show you a simple a case study kind of stuff. So this is a beam. We don't know, a fire happens in a tall building. There are 2 beams, one in one compartment, another compartment. Based on the firefighter reports, based on the reconnaissance, we know that there is damage to the beam, class C or class D. So this is the first fire. I can create the fire in the room if you tell me. That's a different subject. What the fire is, what the contents of the room, whether it's office room or whether it's a hospital room, I can create this. This is a long fire. In another compartment, there is a lot of books and stuff. That's where you have significant fire, longer fire. So if it is, then I do the analysis, first step, second step and third step. Let me go to the second step. So in the second stage of the analysis, you can see this is under the short fire, it's the same beam under the long fire. These are the temperatures in the rebar, these are in the concrete. Obviously, because of the long fire, you have significant level of temperatures in the rebar and stuff. Look at this, how it recovers. Okay, depending on the two different fire scenarios. Okay, so this is the capacity left in the, this is the residual deflection. You need to impose these deflections. What happens? Into evaluating the moment capacity of the beam. So this is under the long fire, this is under the short fire. So if you do a series of calculations, it's possible if there is a bridge under fire. Typically, in the design office, you can do this if you know all the properties of the bridge, which we know, and all the relations, variations in the material properties and others. So number of factors affect this. It has to be given due consideration, including, as I said, the fire scenarios, for example, different fire scenarios. Some scenarios lead you to collapse of the beam or failure of the beam, whereas others to recover. And these recovery, the residual deformations or fire-induced damage in the material itself has an influence on the residual capacity. Okay? So, from this perspective, and same thing, what the load level is, for example, how much load level during the fire is on the beam will influence its response. But you need 3 stages of the analysis, not just checking one core. A lot of times when you take course, you take from one part, where based on it's all your individual intuitions or individual this thing, it may not reflect on that. It's better to look at the global level than at the local level to assess the damage. Okay, so that's why from reconnaissance to advanced analysis, it's very important to apply. And if you see here, I summarize this. Reinforced concrete structures specifically, they retain much of their capacity in most cases, but you need to apply a range of techniques depending on what kind of a structure you have to assess the damage, and that requires from simple reconnaissance to advanced analysis. And 3-stage approach we proposed for evaluating the residual capacity of concrete structures. And following a fire damage, concrete structures, this may satisfy the design limit state, but from strength consideration, but need to provide comparable levels of safety, means you need to retrofit, and for this kind of an analysis is needed. So I would like to acknowledge the contribution from National Academy of Sciences, as well as Michigan State University for this project. This is an ongoing, continuing project we are doing, and thank you all for your attention.